Hey, I'm Ryan, and welcome to NES Hacker. This is the final part of my Better Final Fantasy Shop's ROM Hack coverage. In this episode, I'll explain how I organized the project and cover some of the techniques that I used to finish the hack. Don't worry, it's not rocket science, but it is computer science. In the last episode, I used FCEUX to trace subroutines in the game and make minor modifications to the sale confirmation flow using the debugger. This basic technique is useful for making small changes to a game, but for what I was trying to accomplish, it fell short. Because I was changing how the game worked in some very specific ways, it was really hard to transform the existing code into what I wanted. Mostly, I just didn't have enough space in the ROM to make the modifications that were needed in order to support the features that I was aiming for. In retrospect, this made a lot of sense since I was adding more complex logic to a system that was initially relatively simple. While it's not always true, in general, when you change a simple program and make it more complex, it tends to use more code and thus more space. So in order to proceed, I'd either need to pare down my requirements or somehow find more space to use for my hack code. I was not inclined to change my requirements as that it felt a little bit like giving up. And with my assembly experience, I knew a few programming tricks that I could use to accomplish my goal, given I found the space that I needed. But before we go into the details, help me out by liking this video and subscribing to the channel. After that, we'll go hunting for some unused bytes in the US version of the Final Fantasy ROM. In order to finish my hack, I had estimated that it would require a couple hundred bytes of unused space in order to stash some highly optimized subroutines. On a whim, I opened up the hex editor and started scrolling through the ROM from top to bottom. My idea was to passively search for some larger regions by eye, and then note their exact memory location so that I could confirm that they were unused later. I was nearing the end of Bank 06 when I stumbled across something kinda crazy. I had been keeping an eye out for some small 80 to 100 byte regions that I could use for my more advanced logic. What I didn't expect to find was a 4 kilobyte region of straight zeros at the end of Bank 06. I'd gotten pretty far in the hack by using direct replacements, like I showed in the last video, but I could do some crazy stuff with over 4 kilobytes of contiguous program ROM. Having found a veritable cornucopia of unused space, I devised a method to use said space to great effect. The idea was to fill it with a series of indexed subroutines that could be executed from anywhere in the ROM to change the behavior of the game. Using this approach would make hacking the game considerably easier. Once I had traced the original code that handled some aspect of the game that I wanted to change, I could rewrite the code to call one of my hack routines instead. For the bulk buying hack, I reasoned through the problem and determined that I could make the changes using 4 of these hack routines. The first routine is called when the player selects an item. It would reset the quantity back to 1, then calculate the maximum number of items that could be bought based on the player's gold and inventory space. The routine would store the resulting maximum in RAM so it could be referenced later when performing bounds checking in response to quantity updates. The next routine would handle said quantity updates based on controller input. If the quantity did need to be changed, the routine would update it and also update the total gold for the sale. I'd have the game call this hack routine at the end of the original shop code's controller logic. The third routine would handle the actual buying of items. Its job would be to add the appropriate number of items to the player's inventory based on the quantity, and remove the correct amount of gold. This would be a drop-in replacement for the buying confirmation code that I showed in the last episode. The final routine would render the graphics that showed the quantity and total gold value on the screen. It would be called every frame, but only actually render new graphics if they needed to be updated. With my list in place, I felt pretty good about the plan. The next thing I had to do was figure out exactly how I was going to call one of these hack routines. As we covered in previous episodes, the Final Fantasy program ROM is split across 16 banks of memory. Remember that the game mapper circuitry keeps only 2 of these banks loaded in the CPU memory space while the game is running. The upper half of the memory is always mapped to bank 0F, while the lower half can be switched to any of the banks at runtime. The shop code I was modifying resides on bank 0E, and my new hack routines would need to be placed on bank 06. This meant that it would be impossible to have both banks and thus both sets of code loaded into the game at the same time. So in order to call one of my new routines from the shop code, I'd have to switch from the 0E to the 06 bank, make the call, and then switch back. While not conceptually difficult, this did require a good amount of program code, which was the whole problem in the first place. To solve this, I wrote a subroutine that performed the bank switching logic, executed the chosen hack function, and then returned to the original place in the game code. Then, anytime I needed to modify the game's logic, I'd simply call this method instead of rewriting that whole flow. This minimized the amount of space that I need to make my changes and ultimately made the whole approach possible. In order for this routine to be accessible by all banks, I needed to place it on bank 0F, since it's the only bank that's always active while the game is running. Also, the routine would need a couple of parameters. The first parameter would provide the number of the bank to return to after the hack was executed. This is a bit like jotting down the bank we're on prior to calling the hack routine, so I could have it send us back to where we started when it was done. The second parameter would tell the function which hack routine to execute when called. Basically, all the hack routines are lined up in a big table and are each assigned a number called an index. This parameter tells our code which of those numbered routines to execute. I put the common subroutine into a small unused region that I had mapped out on bank 0F, and after a bit of coding and testing, I was able to successfully execute a basic hack routine. While I think the overall approach is elegant, the details got a little complicated due to the space constraints and how memory mapping works. In the end, it's not that bad, but it can be made a lot more clear by simply stepping through the process line by line. So here's a segment of the original Final Fantasy code that is executed right after an item has been selected. It's at this point that we need to initialize the quantity and calculate the maximum number of items that the player can purchase by calling out to one of my hack routines on bank 06. The first part of the code loads the ID for the selected item into the 6502's accumulator register, then calls a subroutine that finds the price for the item. The results of the subroutine are stored in RAM at memory locations 10 and 11, which are common locations used by the game for 16-bit return values. The second part of the code copies those results to another spot in memory so that the RAM locations 10 and 11 can be reused by other subroutines. Finally, it jumps to a different location in the ROM where the game continues processing the item selection. This is a good spot for me to insert my call. So I replaced the memory transfer code with the instructions to execute my hack routine. In order for the game to operate correctly, we still need to perform the original memory transfer, so I coded the hack routine to do this in addition to all the other initialization. Okay, so let's go ahead and replace the original code with a new code that calls out to my hack function. There. With that in place, let's trace that code to see exactly how it operates when executed by the NES. First, the value for the current bank is loaded into the accumulator, then stored into memory location 00. Next, the index number for the hack function is stored into memory location 01. These two memory locations hold the parameters for the general hack execution routine that I wrote on bank 0F, which swaps to bank 06, executes the hack routine, then swaps back to continue normal execution of the game. With the parameters in place, I then use a JSR instruction to execute my common routine, which is labeled call hack. Now, this is where it gets a little complicated, so pay close attention. The first thing that call hack does is immediately call the swap and jump to hack subroutine, which does exactly as the name suggests. First, it calls a common subroutine to switch to bank 06, then it jumps directly into the execute hack routine that I put on that bank. Execute hack has two primary jobs. The first is to calculate the absolute 16-bit address for the hack function that we want to execute, and the second is to jump directly into that routine so that it can be executed. To calculate the address, the routine uses a lookup table that I also added to bank 06. This table stores the 16-bit addresses for each of the hack routines in a series of byte pairs. The first byte of the pair, called the low byte, stores the lower 8 bits of the address, and the second byte, called the high byte, stores the upper 8 bits. The 6502 in the NES is an 8-bit processor, so when you want to refer to 16-bit addresses, you often have to store and process them like this. To find these bytes in the table, the execute hack routine first multiplies the index provided at memory location 01 by 2. We have to do this because each entry in the table has 2 bytes. The routine then loads the bytes from the table and stores them into RAM. This is so we can use a specialized mode of the jump instruction to move the program counter directly to the address that's been provided. After the jump instruction has been executed, the system will be at the correct location and can begin execution of the chosen hack function. In this case, my initialization routine. Hilariously, the details of the actual hack routine that I wrote aren't all that important for this discussion. Basically, the routine initializes a few RAM locations, such as the starting and maximum quantities, and then executes an RTS, or return from subroutine instruction. It's at this point, when it calls that final instruction, where all that seemingly bizarre direct jumping that we did earlier in the program comes to fruition. Every time you execute a JSR or jump into subroutine command, the 6502 pushes a return address onto the system stack. Then, when executing an RTS or return from subroutine, it pops that address off the stack and jumps back to that location. If you're following along closely, you'll notice that the address on the stack prior to returning sends us all the way back to the call hack routine. This is why we did so many direct jumps, because we had to handle different aspects of the logic required to swap banks and call the function while keeping that address on the stack. Since that address is in bank 0F, which remains fixed, this allows us to return directly to the routine via a simple RTS instruction. At this point, the call hack routine simply loads the return bank that we stored in RAM earlier, swaps to that bank, then executes one more RTS instruction. Again, because of our judicious use of jumps, we see that this returns us directly to where we started. The game then proceeds with execution as it normally would. With this approach in place, making the rest of the modifications of the game was actually pretty simple. Basically, for each aspect of the game that I wanted to change, I just tracked down the original game code in the ROM using the debugger and replaced it with a call to a custom function that I put on bank 06. Honestly, the hardest part of this whole hack was figuring out how to get to this point. Actually writing the code to handle the behavior is pretty straightforward, given you have the space to put the code into the game. So I should have started with this, but let's take a look at the final result, and I can talk you through what's going on behind the scenes. So the first of my custom code runs once an item is selected, specifically while the player is in an item shop. This is the code that we covered in this episode that initializes the quantity and determines the maximum number of items that can be bought. Once an item has been selected and the game has transitioned to the sale confirmation menu, my code then listens for controller input from the player. If the player presses right on the D-pad, then the quantity is increased by 1. If they press left, then the quantity is decreased by 1. It also handles boundary conditions by wrapping the value around if they go past either the maximum that they can buy or below 1. Also, anytime the quantity is changed, my code recalculates the total sale gold, records the value to RAM, and then sets a flag that instructs the game that the gold and total quantity graphics need to be refreshed. Each frame, when the game performs rendering, I added code to check this flag. If it's set, I then have the game execute a custom rendering routine that overwrites the graphics on the screen with updated values. My next bit of code is run when the player confirms the sale of an item. I have the game run a custom routine here that performs the adding of multiple items and removal of the total gold from the player's inventory as a drop-in replacement for the original game logic. Finally, my last bit of code runs when the player exits the shop. This code simply cleans up all the RAM locations that were used by other parts of the code and resets them back to the state that they were in prior to entering the shop. This is a safety precaution as I want to ensure the game goes back to a state that it's expecting when not running my custom code. It's been about 2 months since I sat down and did this hack. Originally, I thought I was going to do a single video on the topic. Clearly, it ballooned a bit on me because I ended up with a 3-part mini-series. Fortunately, or unfortunately, depending on how you look at it, I'm a little tired of talking about all this. So this is going to be the last episode on the topic, at least for a while. I'm pretty happy with what I was able to explain in the last few videos, but there were a lot of details about the hack that I didn't have time to dive into. Either way, I posted the code for my hack on GitHub, and you can use the link in the description to go check out some of those details on your own. Thanks for watching NessHacker. If you enjoyed this episode and this series, make sure you like this video and subscribe to the channel. Click the bell icon if you want to be notified when I post the next video on the channel. And if you have any questions or feedback, let me know in the comments.